Okay, so we're going to look at practice problem number 7 for forces and motion analysis. And it reads, a child starts from rest and goes 22.5 meters in 3 seconds. She's being pulled on a sled with a force of 210 newtons. And the sled and her have a combined mass of 40 kilograms. What is the coefficient of friction acting on the sled? So between the sled and the ground. All right, coefficient of friction. That's a force. Related to a force anyway. It's related to that frictional force. So we're going to start with a force analysis. So what is our object? Well, our object is that girl and sled combined mass. We draw our picture. Well, there she is sitting on the sled on some surface. Let's say she's heading in this direction as she's being pulled. And we're interested in the frictional force, specifically the coefficient, on that object. So we have to look at our interactions. And as we do that, we'll develop our free body diagram. So one interaction, of course, is gravity, and that's between the sled and the earth. And as we develop our free body diagram, we know the force of gravity acts down is equal to mg, which is equal to the weight. She's sitting on a surface, so we know that that surface is getting squished, and we need a normal force. That's between the sled and the ground. And since she's sitting down and pushing down on the ground is pushing back up on her. Now, I'm pretty sure there's no other vertical forces acting, and there's no change in motion in the vertical direction, so these two arrows should be the same. Okay, other forces. Well, she's being pulled along, so we know we have the force of the pull. And that's between the sled and the puller. And we said she's moving into the right direction, is going to be starting to move in that direction or accelerating in that direction. And so we have the force of the pull to the right. And then we want to know if she is, what the frictional force is. So we know that there's a frictional force. We want to think about, is that friction kinetic or static? Well, she's moving, accelerating. She's going from rest to 22.5 meters. Since she's sliding, it's got to be kinetic friction. That opposes the motion. We said the motion was to the right. So kinetic friction is going to be to the left. And why did I draw that arrow a little bit shorter? Well, these are the only two forces acting in the horizontal direction. And I know she's accelerating to the right. I set her motion to the right. She's going from 0 to 22.5 meters, starting at rest, so she has to be speeding up and moving to the right. Says my acceleration is to the right. If my acceleration is to the right, the forces causing it are to the right, and therefore the rightward forces have to be bigger than the left. All right, so now we separate these forces into their horizontal and vertical components and analyze them so that we can see what that coefficient is. So I'm going to put those up here with 4 forces, horizontal and vertical. Our first force is the force of gravity. It's purely down, nothing horizontal. So we have minus Fg. That minus is indicated by that downward arrow. Our second force is the pull. It's pulling us to the right. So we have a positive force of the pull and nothing vertically. Force number 3 is acting straight up, that normal force. So we do not have any horizontal component. The positive is up, and we see that normal force. And force number 4 is our frictional force. It is acting to the left, so it's negative, and there's nothing vertically. So we've identified every force on our free body diagram into its respective horizontal or vertical motion, or influences. We know by Newton's second law that the sum of the forces horizontally is the mass times the horizontal acceleration, and the sum of the forces vertically is the mass times the vertical acceleration. I'm interested in figuring out the coefficient of friction for the horizontal motion. So I'm going to start with the horizontal motion. I have the force of the pull minus the force of kinetic friction is equal to the mass times the acceleration horizontally. Okay, well, I know that the force of the pull is 210. I don't know the kinetic friction because I don't know the coefficient. We want to keep in mind that our kinetic friction is equal to mu times n. The kinetic coefficient times the normal force. I want that coefficient. So I'm going to input this relationship into my equation so that I can solve for the coefficient. Mu. Oh, but I only have an n in my list. We'll come back to that. The mass of the combined sled and person is 40, and I don't know the acceleration. So I'm missing a lot of variables. One I know I'm missing, it's the one I want. But I'm also missing the normal force and the acceleration. So let's see if we can find the normal force. Still forces, and I'm still within my analysis. Well, the normal force is acting in the vertical direction. So maybe I can analyze the sum of the forces in the vertical direction. Well, if I add those forces, minus Fg, plus the normal force, I get the mass times the acceleration in the vertical direction. But the object's not moving up or down. So that's equal to 0. And I find that my normal force is equal to Fg, which we know is equal to m times g. So my normal force is 40 times 9.8, or 392 newtons. So I can at least pop that back in to my normal force. It's the same normal force that's involved in friction. And I have 210 minus mu times 392 is equal to 40. I still don't know that acceleration. So I'm not going to get acceleration from my force analysis because it's in the horizontal direction. I don't have enough information. But if I need acceleration, I could maybe describe it through the kinematics process, since after all, it's that force that causes that motion. So let's look at the kinematics of it. Now that requires us to set an origin. So I'm going to go back over to my picture. I'm going to put my origin at the start of the sled. When does the motion I care about begin? When does the motion I care about end? This is going to help me generate that list of variables, that list of descriptors. So at the beginning of the motion is when I'm just starting to pull. When the motion starts to move. And the end is after I go 22.5 meters, which of course happens in 3 seconds. So at the end of 22.5 meters, or at the end of 3 seconds, they're one and the same. So that's when I quit caring. So if I make my list, initial and final positions, initial and final velocities, acceleration, and time. My initial position when I start moving is at the origin. Final position, 22.5 meters. My initial velocity, it says I'm starting from rest, so that's going to be 0. Final velocity, I don't know. Acceleration, I don't know. But my time is 3 seconds. So the reason I went after kinematics is because I was interested in, of course, acceleration. Now both equations that I use in kinematics have acceleration. So how do I pick it? Pick the one that I know the most information to begin. And that's final position. So x final equals x initial plus v initial t plus 1/2 at squared is going to be that equation that's going to be helpful for me. My final position is 22.5 meters. My initial position is 0. My initial velocity is 0 times my 3 seconds plus 1/2 my acceleration times my 3 seconds squared. So I end up with 22.5 is equal to 4.5 times the acceleration. And I find that my acceleration is equal to 5 meters per second squared. So now I can use my acceleration in my relationship, and I can solve for mu. So we have 210 minus mu times 392 equals 40 times 5. And doing that algebra, we see that 210 minus mu times 392 is equal to 200. Minus mu times 392, bringing the 210 on both sides, is equal to minus 10. And we see that mu is equal to 0.03. It's less than 1. That's a good thing. It needs to be less than 1. Greater than 0, because we know there's some friction, because we're looking for that coefficient. And we determine our coefficient. So, we needed our coefficient. That's a force. Look at the force analysis. Force analysis, in the horizontal direction is where that friction is acting. We realize we are missing both the acceleration horizontally and the normal force. The normal force is related to the vertical motion because it's acting in the vertical, the vertical forces, it's acting in the vertical direction, so I can use my vertical forces to get that normal force, but I'm still missing the acceleration. Acceleration, of course, is a descriptor. So let's look at our descriptors, and we can use our descriptor of motion to find that acceleration, ultimately getting our coefficient. Long process. The physics guides you through it as long as you keep going after what you're interested in. Good job.